Hello and welcome to this course on gas turbines and jet engines. Okay. So, today is lecture 9 of this course. So, this is the fourth lecture of the second week of this course. And today we are going to learn gas turbines or gas turbine cycles with intercooling, which is a new type of cycle that we are going to learn today. Okay. So, the concepts that will be covered are what is Brayton cycle with intercooling or simple gas turbine cycle combined with intercooling, as well as what are the optimal conditions and performance, how to calculate the performance characteristics of this intercooled cycle or intercooled Brayton cycle. Okay. We will also find the optimum value of or optimum condition for which we get the maximum work output from the cycle. Okay. What is the intercooled Brayton cycle or what is the intercooled Brayton cycle? Okay. Before I discuss the component diagram, let us first quickly try to understand what is the reasoning or what is the concept behind this, why this has been developed. Okay. Let us consider a simple TS diagram. Okay. So, we will draw a normal TS diagram on the right hand side. So, for an ideal gas on a TS diagram, we know that constant pressure lines diverge towards the right hand side, which means that if I have say if I have a compression process occurring starting from low temperature, okay, the work input that will be required for this process is going to be lower as compared to another compression process for the same pressure ratio, okay, going from P 1 to P 2. For the same pressure ratio, the work input will be higher if we start at a higher temperature, because the constant pressure lines are diverging. Okay. So, I leave it up to you to think and find the reason why constant pressure, or how can you prove that constant pressure lines are diverging, okay, based on your knowledge of thermodynamics. Anyway, so we see that if we can somehow lower the temperature at which the compressor operates or part of the compressor operates, it will be possible to decrease the amount of work that is required to run the compressor. Okay. So, the intercooled cycle has been developed with this idea or with this concept, keeping into consideration this concept, the intercooled cycle has been developed. So, how does the intercooled cycle look like, or what is the, let us say, how does the processes of an intercooled Brayton cycle. So, all these cycles are different modifications of Brayton cycle. So, I am omitting the term Brayton cycle in some cases, but from the context it should be clear that this is intercooled Brayton cycle. So, let me first draw the cycle, then we will come to the arrangement of the different components. So, we have a compression process going from 1 to 2, but here unlike all the previous cases that we have seen, all the previous 4 cases, the entire compression is not done by this compressor. So, this is known as low pressure compressor. So, this operates at lower pressure, it is taking the ambient air to some intermediate pressure. Okay. Then the air at intermediate pressure, which will have somewhat higher temperature because of the compression, the temperature can significantly increase in compression, right. If you remember the previous problem solved in the previous classes, before compression you can go back and check the values. Before compression the temperature was 300 Kelvin, after compression it was 500 something Kelvin. So, more than 200 degree or 200 Kelvin rise in temperature was there, okay, which then which translate to significant amount of work input. So, this air after partial compression, this is again cooled back, okay. This is again cooled back, and such that we come back to the same temperature. It need not be always be same temperature. I will explain why I am saying we come back to the same temperature. So, this cooling is done by using a heat exchanger So, the air is cooled and this heat exchanger typically works by using water at ambient condition for cooling the air. Okay. So, after this there is a second compression process going from 3 to 4 to take the partially compressed air to the required combustion chamber pressure or the turbine inlet pressure. Okay. So, up to 4. Then the normal heat addition or the combustion process occurs. Then we have the expansion in the turbine. Okay. So, 4 to 5 is the heat addition combustion, 5 to 6 is the expansion in the turbine. Let us say that 6 is somewhat lower, as will be the case. And then from 6 to 1 we close the cycle. In actual application the exhaust gas will go out to the atmosphere at state 6, but in the ideal case we are closing the cycle. We close the cycle by adding a hypothetical heat removal like for all the other cases constant pressure heat removal process 6 to 1. Okay. So, this cycle is known as intercooled cycle. Let us again quickly go through the important parts. 1 to 2 is the compression process. Okay, 1 to 2 we know already as compression. In this case this is the low pressure compression. Low pressure compression, okay, because the pressure range is lower as compared to the other process. Then 2 to 3 this is the intercooling process or heat exchange process. Some places this or some books it may be written at heat exchange or heat exchanger, but intercooler term for the device and for the process intercooling is more suitable. The device is known as intercooler, okay, and the process is intercooling, which is a type of heat exchange process of course, where heat exchange occurs from cold means from the hot air at the exit of the compressor. So, from there heat is removed by the cold water, okay, circulating through the heat exchanger. Cold water air, by cold water I mean that water which comes at ambient conditions, because there is no point in using some work to reduce the temperature of water further, because that will anyway not lead to net work increase. Okay. So, this 2 to 3 is the intercooling and the device is known as intercooler. Okay. Device is known as intercooler. Then 3 to 4 is the high pressure compression process. Okay. 3 to 4 is the high pressure compression process. So, this is the high pressure, this occurs in the high pressure compressor, because the pressure range is here considerably higher. Then I will not write down the rest of the process, because we already know these processes. 4 to 5 is the combustion process or constant pressure heat addition, 5 to 6 is the expansion process in the turbine. In this case we are not considering reheating. So, it is a single expansion, cumulative single turbine expansion process, and 6 to 1 is the so 5 to 6 is isentropic expansion of course, and 6 to 1 is constant pressure heat removal. Remember that all this compression process 1 to 2 and 3 to 4, for ideal cycles these will be isentropic processes, isentropic compression process, isentropically rise in the pressure. Okay. Now, why did I say that T 1 should be equal to T 3 typically, or T 3 should be equal to T 1? Because we will use a coolant, typically this is water, so that the process is inexpensive. This water will be at ambient condition. So, we cannot cool the air below ambient temperature. So, theoretical limit is that we reach the ambient temperature, which is the temperature at state 1. Okay. So, as a result, for the ideal cycle we have T 3 equal to T 1. Now, T 4 and T 2 can be different, it depends on what pressure is used for the intercooling. Okay. So, later we will see that there is an optimum pressure for intercooling, and we have to find this optimum pressure, for which we get the maximum work output from the cycle, which translates to minimum work input to the compressor. Optimum pressure of intercooling. Okay. So, what is the net result of this? Okay, what is the net result of this? The net result is that the overall work, actually work input decreases, not the overall work input to the compressor decreases, because now we have a compression process which occurs at lower temperature. The second part occurs at lower temperature as compared to, although it is not apparent from the diagram, as compared to the original case, which would be corresponding to this red line. Okay. Corresponding to that, now the heat the work in addition needed is much lower. Okay. Because the constant pressure lines are diverging along this, we can calculate and see that this is the case. Okay. Instead of this original red line, we are shifting this to a lower temperature process. So, we expect that the work input will be lower to the compressor or the compression process. Turbine work input remains similar, okay, which means because the pressure range is same as a simple Brayton cycle, which means that the net work output should increase. Okay, net work output should increase. However, this also comes at the cost of efficiency, because now we have a added section of heat addition. So, more heat addition is needed in the combustion chamber. So, we expect that because although the network is increasing, the net heat addition not this heat addition, additional heat addition which is needed, this will balance the effect and efficiency may be lower, but the main idea behind intercooling or using an intercooler is to increase the net work output, similar to a reheater. Okay. So, how does this look like, this arrangement of the different components? So, if I compare this component diagram, which I have taken from the book by L. Syed Ahmed, if I compare it with this TS diagram. So, from 1 to 2 is the low pressure compression process, then 2 to 3 is the intercooling or the heat exchange in the intercooler. Okay. Here the heat is removed to an external source. So, it is not like regeneration. Okay. Here the heat is being removed to an external circuit. So, external water. So, we are just removing heat from the cycle. Okay. So, from there then we reach state 3, and from state 3 again there is the second compression process, okay, and we go to state 4 okay, after the second compression. Then from 4 to 5 is the heat addition in the combustion chamber, 5 to 6 is the expansion in the turbine, and in the actual cycle the exhaust will occur at state 6, but we are closing the cycle or closing the loop by assuming that this 6 is connected to 1, and there is a constant pressure heat removal. Okay. So, this is the cycle. So, couple of points that I should discuss here, or we should remember here is that, one is that because we are adding a heat exchanger and there is heat exchange between liquid, so liquid water and air, the size of the device or the heat exchanger is quite bulky, okay, as compared to say all the previous processes. Regeneration, it can be done at high speed, both the gas flows can occur at high speed, and there is no external source of any additional fluid needed. Okay. Similarly, in reheating also combustion can occur in a small footprint. On the other hand, this heat exchanger addition for intercooling is both bulky as well as it makes the circuit or the cycle not self sufficient. So, you now need continuous supply of water to the cycle to run the cycle, okay, unlike the previous cases. So, this makes the cycle depend on external supply of water. So, these are some of the drawbacks, but this weight and the supply of water is not a very restrictive condition if we think of power generation gas turbines. So, gas turbines which operate as industrial gas turbines for power generation, because there it is installed at a certain location and just fixed there. So, both the weight and the power means water supply is not a problem. However, this type of systems intercooling cannot be used with gas turbines where weight is of very high importance, such as for jet engines, as we will see later. So, jet engines we cannot use this type of modification. It is anyway not possible to continuously keep on supplying water also. Okay. So, this should be also kept in mind. So, now we will analyze this intercooled Brayton cycle. So, we will again draw this TS diagram, okay, because that is our starting point for all the cases. So, as we have seen, for this intercooled Brayton cycle or intercooled cycle in short, we have the process going from 1 to 2 high pressure low pressure compression, then from 2 to 3 is the intercooling process, 3 to 4 is the high pressure compression. So, the intercooling has divided the compression process into two parts, as we have discussed in the previous slide, and then from 4 to 5 we have the heat addition or the combustion process. So, heat addition in the combustion chamber. 5 to 6 we have the expansion in the turbine, and with 6 to 1 we close out the cycle by adding the hypothetical heat removal process at constant pressure. So, this is our TS diagram, and here the intercooling is the process going from 2 to 3. Intercooling is the process going from 2 to 3. So, now to analyze this, we will define some parameters. Some of them are already we have used. So, for example, we know that the temperature ratio T is defined as T 5 by T 1. Okay. So, in this case T 3 is also equal to T 1. Okay. T 3 is also equal to T 1. Why T 3 is equal to T 1? Because in the intercooling or in the intercooler, the cooling is done by taking water from ambient conditions, okay, because it does not make sense to have refrigerated water, which itself will need some work to use in an intercooler to reduce work, because already you need to supply some additional work there. So, generally the inexpensive water available at ambient condition is used in this heat exchanger. So, the minimum value to which the temperature of the air in this case can go, theoretically it can be as low as the ambient temperature T 1. Okay. So, this also means that T is equal to T 5 by T 3, but let us keep it like this. Now, we will define the overall pressure ratio P 5 by P 6, as usually this is equal to R as usual, okay. And then C is defined as R to the power gamma minus 1 by gamma. Okay. Now, each of these individual compression processes, low pressure compression, let us say this process, we can associate one compression ratio for this. So, let us say that is R A. So, R A is equal to P 2 by P 1. Similarly, R B is equal to P 4 by P 3. Okay. So, which means that if I combine these two together, R A into R B is equal to P 2 by P 1 multiplied by P 4 by P 3. Remember that P 3 is equal to P 2, because it is a constant pressure heat removal in the intercooler, right. So, P 3 is equal to P 2. So, this means that this is equal to P 4 by P 1. What is P 4 by P 1? P 4 by P 1 is the overall pressure ratio, P 4 equal to P 5 and P 1 equal to P 6. So, this is the overall pressure ratio R. So, which means that R A into R B is equal to R. So, this is similar to the case of reheating or reheated Brayton cycle, but in that case the pressure ratios were defined for the turbines, two turbine expansion processes. Here the two pressure ratios are defined for the two compressor processes, two compression processes done in the low pressure and high pressure compressor. So, corresponding values of C also can be defined. So, similarly, C can be defined C A, which is for the process going from 1 to 2. This is equal to R A to the power gamma minus 1 by gamma, okay. And C B is equal to R B to the power gamma minus 1 by gamma. So, from this relation already which we have derived, we can also obtain that overall ratio C is equal to C A multiplied by C B. Okay. So, this is also a very useful relation, and this is again similar to that of the reheat cycle, but here again the ratios are for different quantities. So, these are the temperature ratios. So, R A to the power gamma minus 1 by gamma is what? So, this is the temperature ratio T 2 by T 1. Okay. So, C A is equal to T 2 by T 1 and C B is equal to this temperature ratio T 4 by T 3. So, this is equal to T 4 by T 3. Okay. So, if we multiply both the temperature ratios, we get the overall value of C. Okay. So, these are the parameters which are defined. Now, it is not known to us at this point how C A and C B are related, apart from the fact that C A into C B is equal to C. Now, whether we are going to divide this as, say, if the pressure ratio is 10, okay, if R is 10. So, whether R A will be 2 and R B will be 5 or R A will be 4 and R B will be 2.5, that we have to we have not yet fixed. Okay. Later we will do an optimization and we will find that there is a particular set of values of R where we get the highest work output, okay. And this is almost similar to the case of reheating or reheat cycle, where the highest value of work output is obtained, highest value of overall work output or lowest value of work input to the compressor is obtained when this R A is equal to R B equal to root R, that we will derive in the next class. Okay. So, anyway, C is equal to C A into C B. Now, let us analyze the cycle. What is the value of W net expression? So, net work output is C P T 5 minus T 6 minus, there are two compression processes now, we have to consider both of them, minus C P T 2 minus T 1 minus C P T 4 minus T 3. Okay. So, in non-dimensional form, we need to divide this W net by C P T 1. We obtain, so C P gets cancelled, we obtain T 5 by T 1 minus T 6 by T 1 minus T 2 by T 1 minus 1 within bracket minus T 4 by T 1 minus T 3 by T 1 within bracket again. Okay. So, what are these individual values? T5 by T1 first. So, T5 by T1 we already know, we have written here also that this is equal to T. Okay. So, this means that the first term in W net by CPT1 is equal to T. Then T6 by T1, this value by this value. So, let us find this T6 by T1. Okay, let us use some other color, so that we can distinguish between this. So, T6 by T1, we can write this as T6 by T5 into T5 by T1. Okay. So, T5 by T1 or T6 by T5 into T5 by T1. Why we have written in this form? Because now we can easily express this in terms of C and T. Okay. So, what is T5 by T1? We already know that is equal to small t. Okay. What is T6 by T5? T6 by T5. Okay. So, T5 by T6 we know is equal to r to the power gamma minus 1 by gamma. So, T6 by T5 is 1 by r to the power gamma minus 1 by gamma, which is 1 by C. Okay. So, this is equal to 1 by C. So, in total then this becomes T by C. Okay. So, T minus T by C we will write here later. Then we will have to find T2 by T1. What is T2 by T1? T2 by T1 we already know, this is equal to Ca. Okay. T2 by T1 is equal to Ca. Then what about next term? Next term already we know it is 1. Then T4 by T1. What is the value of T4 by T1? T4 by T1, because T1 is equal to T3 or T3 equal to T1, T4 by T1 equal to T3 by T4 by T3, and we know that T4 by T3 is equal to Cb. Okay. So, we get this ratio as Cb, and then finally, T3 by T1 which should be equal to 1. Okay. So, we are going to replace all these values here. So, and get the final expression which is T minus T6 by T1 T by C, okay, minus T2 by T1 Ca minus 1 minus T4 by T1 Cb minus 1. So, this is the expression for net specific work output in non-dimensional form, where this Ca and Cb can be different, and but the product of this Ca and Cb is equal to C, and T is the temperature ratio. Now, if we want to find an optimum value of Ca and optimum value of Cb, we can take a derivative of this net work output with respect to any of these two variables, either Ca or Cb, because both are related. We can, for example, take a derivative with respect to Ca, and we can obtain what should be the relation between Ca and the other known quantities T and C. Okay. That can be done, which we will do in more detail in the next class. We can take a derivative, okay. For that we can take a derivative of this net work output by CPT1. So, non-dimensional net specific work output with respect to any of these parameters Ca or Cb, because they are not independent. Cb is equal to C by Ca. So, we are going to take a derivative with respect to Ca and equate it to 0, and from there we can find a condition for which, or an expression for Ca in terms of known parameters C and T, so that we know what should be the optimum case. Okay. So, I think we will stop here today, because we are running out of time in today's lecture, and we will continue finding this optimum value. So, optimum intercooling we will find in the next lecture, and then we will solve a problem to see how to do calculations for this type of cycles. Okay. So, we come to the conclusion. So, to summarize, in this case we have analyzed the Brayton cycle with intercooling. However, we have not yet derived the condition. We know how to derive the condition now for optimum intercooling, and we know that optimum intercooling will be there present, and we know how to start deriving it, and we will derive it in the next class. So, with this we will conclude. So, these are the references. One of the images is taken from the book by L. Syed Ahmed as shown in the previous slide, and the other textbooks are also for reference. The material is prepared by consulting all these books. So, with this I end the class today, and thank you, and we will meet in the next lecture. Okay. Thank you. We will stop today. We have seen, to briefly summarize, we have seen how to analyze combined regenerative reheat cycle, compare the values of standard Brayton regenerative reheat and regenerative reheat cycles for same design parameters, and along the way we also learned the procedure to solve numerical problems for regeneration reheat cycle problems. Okay. So, these are the references, and with this we end our class today. Thank you.